Just wait one more person. In fact, several days ago, Sashadar came to my house and established somehow this internet connection, virtual personal network, VPN, yes. And till then I had no idea how it is registered. And yes, I checked that it is registered, and it's bits so the letters are not so clear somehow because of the whiteboard. Blackboard is not clean. And there are more than 100 persons who follow. 100 persons or hundreds, maybe one person can say check several times, of course. It doesn't mean that there was that, but yes, I was very amazed. Yes. I don't know. Yes, there are persons who follow this lecture from Skolte of other institutions, and there are aspirants, PhD students who wish to follow from St. Petersburg, and so on. So yeah. So it is meaning, even though there are only few few persons who follow this lecture in person, but potentially there is the audience can be larger somehow. And maybe yes, when this register is ready, is it so? Do you begin it?
Yeah, it's
It works already. Okay. It works, yeah. Okay. Yeah, so, and today, till last lecture, I explained theory of Gauss hypergeometric function and so-called Schwarz map, Gauss-Schwarz theory. The file I sent all of you, the book by Masaki Yoshida, Fuchsian differential equations. I hope that everybody got it. If somebody did not get any file, please tell me. I shall send you the PDF file of the lecture. Okay. So maybe not necessary. Every person follows the lecture in person. And today, it is the classical one. How to say 19th century, very well developed theory on the period integral of algebraic curves. With that can be understood as branching covering of 4 points: 0, 1, 1 over z, and infinity. 4 points. Typically, it was elliptic curve. The first simplest case was that. Today, from now on, there is 1 month. Room for us to discuss some rather higher order hypergeometric function that is called Yokohama hypergeometric function, theory of Yokohama hypergeometric function, the higher order. So it is generalized. First, we define a generalized hypergeometric series. It contains 2k minus 1. Let k be some integer. Maybe more than 2. Yeah, that more than 2. And it depends on in general complex, but rational parameters that is defined in the following manner. That is a series till k. I have k parameters, alpha 1, alpha k. Say alpha 1, alpha j, beta j, there some integer, more conditions are imposed further, times z power m. Here I denoted alpha m. This is Pohama symbol. So Pohama symbol, Pohama symbol. That was that we already used, of course. All the time we used m minus 1. That is equal to gamma of alpha plus m over gamma alpha. When alpha is not, when it is well defined, when alpha is not negative integer. Okay. So this is the notation. So I have beta. In fact, from now on, everything depends on pair of 2k tuple of rational numbers, these parameters, alpha j, beta j, that I denote I shall further use okay. So alpha, there alpha j and beta. So beta from now on, beta k. Beta k. It is always 1. So in fact, it is. It depends on two k parameters. 2k parameters, but one parameter is fixed. In fact, this situation, Gauss case, alpha, beta, gamma of z, this is exactly what was written before. Alpha, m, beta, m, gamma power m, and so 1 is lacking, so 1, beta 2, you say. So 1, this means that comes from 1, no m, yeah. If you put, yes, alpha 1, then you get m factorial, z to the power m, and this is Gauss case. Okay, so in fact, this notation. Maybe it's better to write. Also recall that this can be written in the following manner also, with the aid of gamma function. With the aid of gamma function, that is, say, it is equal to infinity product of key parameters divided gamma beta j plus m, gamma beta j, gamma alpha j, everything, and z to the power m. So this series is convergent open disk. This can be seen immediately by D'Alembert. D'Alembert test will give you the ratio of two terms, so z m plus 1 term and the m term is easily calculated because of this alpha over m plus 1 alpha m is nothing but alpha plus m, isn't it? Yes, m plus 1. So this relation entails that the ratio of this m plus 1 term and m term will give you alpha j plus m, beta j plus m times z, and this will go to goes to z as m tends to infinity. N tends to infinity. So this is this must be smaller than 1. So that is say convergent in this open disk. Now, so the argument is absolutely parallel to what has been told on Gauss hypergeometric function. Now, let me fix some notation. Say alpha, I have this k, beta also, and beta k, always assume beta k, assume that all the time beta k be 1. And the condition that I impose is the following, that they are not integer, and beta j not integer except last one, k minus 1, last one. So the condition, some conditions on, so let us call it a non-resonant condition. Non-resonant condition. So first one, the second, and also I impose that the difference beta j minus, I think that beta j minus alpha I, not in k, not in z, for all to the moment, so nothing. The difference between these parameters never turns out to be an integer. So that is, say beta 1, it comes, yeah, from this condition it follows. So it's somehow redundant that from this condition, third condition to second condition follows. Sorry, the first condition follows the first condition, because beta k minus alpha I never be beta k is 1. That is, say alpha I cannot be also an integer. That follows. Yeah, but in any case, yeah, to somehow, for the sake of simplicity. Okay, under such condition, under such that I call non-resonant condition, and it's somehow cumbersome to write this this expression all the time, alpha 1, alpha k, and so on. So let me introduce a notation that f, say, alpha beta z. Yeah. So alpha beta is a vector, k vector, two k vectors of parameters. So that's a notation that I use. This notation I will use further in order to avoid a cumbersome notational difficulty. So in any case, we have little time. And the first result on the now we ask what is the hypergeometric equation, Pohama hypergeometric equation that is satisfied by this series. Convergent, that is it's a holomorphic solution. It's a holomorphic function inside of this open disk, and this satisfies, this holomorphic function satisfies ordinary differential equation that can be written down in a following manner. So let me denote. Okay, so the answer is the following. That I introduce the following differential operator that depends on 2k parameter sets. That is defined in the following manner: that z times equals z times product of first order operators minus this operator, where theta z is always z times ddz. Z times ddz, as before. So this is somehow definition. Let us introduce this operator. Then, so if this series holomorphic function on an open disk turns out to be a kernel of this differential operator, that is, say, d alpha beta f alpha beta so first proposition. So in the case of n equals 2, k equals 2, it's exactly correspond to Gauss hypergeometric. Sorry. So minus 1. Sorry. Minus 1. Yeah, there's some shift. Shifts. In fact, if you want z put here. I think that it will be so what is it? Z theta z plus lambda alpha equals theta z plus what? Alpha minus 1. So let us z to the lambda plus alpha. Yes, alpha minus 1 times z. You see this? So to verify it in a simplest manner, don't open it. You shall not open it. So apply this operator to z to the power lambda, everything. Then you get this is z times lambda plus alpha. Lambda plus alpha times z to lambda plus 1, lambda plus 1, yeah, lambda plus 1. So, and you apply, so z lambda plus 1, after application this differential operator will give you exactly the same lambda plus alpha, lambda plus 1 plus alpha minus 1, this coefficient, and exponent and lambda plus 1, the same. That is, say, for every lambda it's true, then every, in function analytical consideration that this equality always holds. This operator so you get, if you put here, you see that alpha j minus 1 will appear. Oh, okay. That is, say, somehow, yeah. And this situation helps you to understand the reducibility of the monodromy of this the solution space to this differential equation. In fact, somehow this condition, non-resonant condition, somehow excludes such kind of reducibility. This somehow ensures that I will tell you in further lectures. So this series as a function holomorphic and a small and an open disk a function satisfy this differential equation and yeah, so maybe I can tell you how to prove it. It's a very simple, but to get somehow the number of parameters grew from 2 to any k, so maybe it's useful to verify this relation as a solution in terms of recurrence relation between coefficients. So the proof is of this relation. This sharp equation. So let us apply this operator, this first operator and second operator. First operator, both of them has degree k. That means that it's a Fuchsian differential equation, so called. So first one, that let us apply this operator to the series, to this series. So what happens? So it is. So it is this alpha j m beta j m 1 to k and z to the power k. Apply, and you immediately see that this will give you z times. So it's absolutely conversion, so we can differentiate term wise, m plus, m, of course, it's serious. So theta z plus alpha j, if I apply this, then we get m plus alpha j times alpha j and Zm, okay? So I have Z here, I put it here, then 1 plus 1, and then, so this one is nothing but alpha j n plus 1, isn't it? After this, the definition, yeah. The definition. So now the index shift happened with numerator, and now thank you, clear. Yes, it fell down, and so left hand side. Right hand side, apply this operator. Theta z plus beta j minus 1 to apply this, the same thing, the same series. The same series, eh? So this time, what happened the same. That is, say, it will be now. So this factor, and so alpha j, it doesn't change, and times beta j plus m minus 1 divided by beta j m. Okay, but beta j m is beta j m minus 1 times beta j plus, wait a minute, beta j, where is it? Yeah, so beta j m minus 1 m minus, yes, m minus 1. Okay. So that is beta j m. And they cancel, of course. And m and z to the power m. So both of them are equal. So simply you consider m m2, say m prime, that is m prime plus 1, m prime plus 1, and m prime larger than 1, larger than, what happens? M prime equals m prime plus 1, okay, yeah, m prime is larger than 0, 0, yeah, the same thing, yes, sorry. So these two series coincide. So this is somehow a relation between a recurrent relation that is valid, that holds between subsequent coefficients. So in other words, hypergeometric series is somehow characterize this kind of relationship. Yeah, this kind of the ratio between two coefficients is expressed by means of rational function in M. So the main idea is the following: that alpha j m plus 1 beta j m plus 1 divided by mm. It is, of course, alpha j plus m minus 1 divided by beta j plus m minus 1. M plus 1, so m. J equals 1 to k. So there are two. This is very nice situation. That is, say, there is a linear function, alpha m. Say, I can say linear function. It's a rational function defined by product, each of denominator, denominator and numerator and denominator are linear function of the same degree. Degree in t, and t equals m. Degree t in p equals degree in t of q. Equals k, isn't it? Equals k. So this situation somehow reflects quite many important properties that can be generalized to other cases. So in fact, this is some regular singularity Gauss, yeah, not Pochhammer hypergeometric equation is regular singular differential equation. And in algebraic geometry, everywhere you see. So periods are regular with area singular, Gauss-Mann system solution, and so on. This is this kind of thing. One side of this. The other one is that this linearity, these linear functions, they bear kind of so you can consider the zeros of this polynomial function or pole of this rational function. That will give rise to the notion of filtration, Hodge filtration, so Newton filtration, and so on of D modules. In fact, it is also filtration on D module. Newton, maybe Saba uses Newton. Some people use Hodge filtration. In any case, it doesn't matter. Some filtration D module that has been developed by Bernstein, Gelfand, And Deline, of course, Deline worked much on this. So on. So this is this case, our quite simple situation, give you some insight into the more general settings. That's somehow used in a very to the moment not quite unified manner. So I'm proposing you to study this kind of vision and in a unified manner to do further more unified mathematics. Okay, so in fact, so this was first defined as a series, simple analogy of Gauss hypergeometric equation, Gauss hypergeometric series. But and it was so Gauss hypergeometric function was we understood that when alpha beta gamma are non-resonant rational numbers, then we can understand it as a period of super-elliptic curve. Certain curve y to the power m equals xa 1 minus x b 1 minus z x some c, this kind of periods. Integration of cycle upon cycle over y dx y of something, y to the power something of dx. This was the expression, so it depends on z. Y, okay, y z. After different, this was our situation. Now, a similar thing is valid. It is natural to expect that this series also can be expressed in terms of integral over certain algebraic variety. But so in the Gauss case, it was simply a curve, algebraic curve, M covering. So this situation, in this situation, it is rather higher dimensional. We need to take into account higher dimensional variety. So let me introduce the following differential form. Let me consider differential form k minus 1 differential form. So k minus 1. That depends on alpha and beta. So it is x1 to the power. So it is differential form on algebraic variety. An algebraic variety that shall be somehow precise. So first I write down a formula. The definition of this: beta 1 minus alpha 1 minus 1 etc. And x to the power k minus 1 to the power alpha k minus 1 minus 1 minus beta p minus 1 minus alpha k minus 1 minus 1, and then I shall add a term that depends on z, deformation parameter, x1 x k minus 1 to the power minus alpha k. Alpha k dx1 dx k minus 1. Such a form. That is, I can write it in a, shall I multiply by something? No. Okay. So, definition, I can write it down in a more. 1 to k minus 1, xj, alpha j minus 1 minus xj, beta j minus alpha j minus 1, isn't it? J runs from 1 to k minus 1, and the last term will be z minus z times product of all these and power minus alpha k dx so this I impose this non-resonant condition. Yeah, these are all these are also not integer. For the sake of simplicity, you can consider some small positive rational number. With this one also, positive rational number. So, what was the if I recall the Gauss hypergeometric integral? It was like this, x to the power beta minus 1 minus alpha dx. That was our integral that we integrated along a Pohama cycle. That I denote 0, 1 covering over 0.01, 0, 1, these branching points of this integrand function. So, in fact, it is true that this value, this series, can be understood as integration of this differential form, that has finite branching over every branching loci, xj equals 0 and 1 xj 0 equals 0, and this one somehow. So that is small parameter. And the answer is, welcome, the following, that if I integrate this, so instead of integrating on a cycle, in fact, if so I recall you that how I constructed how I construct constructed this Pohama cycle. Pohama cycle is constructed in a so 0 and 1, x 0, 1, and these are branching points of this integrand function, and we constructed first like this, so turn around like this and like this. So first and then I must turn back and then go to the same so the important point is that in turning around these branching points, I need to choose a path that cancel these angular change factor. Once counterclockwise, then otherwise clockwise, and then if I do like this, then the path will be closed. It will come back. The integrand function will recover its initial argument. So that was the way how 0, 1, this 0, 1 interval, from 0, 1 interval, we constructed Pohama cycle. Pohama cycle that can be considered as on this, where is it? Yeah, this Algebraic curve. Maybe VZ on the curve. So we do somehow a similar thing in a higher dimensional case, but instead of discussing about Pohama cycle, it will be quite too much ambitious to the moment. So I simply propose you to look at interval along intervals, product of intervals, 0, 1 intervals. Yeah, 0, 1 intervals. So 0, 1 interval, I have it's so x1 to xk minus 1. I have k minus 1, product of k minus 1. This is the domain integration. No? And I integrate this so k minus 1 form, on a real simplex, say, then it will give us and if I regularize somehow k minus 1 over so the important thing is that you shall feel somehow regularity structure that appears in this formula equals f this Pohama hypergeometric series. Okay, so this is it is equal to 0, 1 k minus 1 times dx1 to dx k minus 1. Yeah. In fact, this part is so I think that is quite small. That is, say, this branching, yeah, loci is quite far from 0, 1. You can assume it. Like in the case of, in this case, 1 over z was somehow other. So of course that is not equals to 1. Okay, so this relation is somehow instructive. If you succeed to generalize this result, this is also already, so this, if you say, suppose that now we can find this algebraic variety. This algebraic variety must be of this form, isn't it? Y to the power m equals x to x1 a1 1 minus x1 b1 and so on, x to the power xbk and these rational numbers can be these integers can be recovered from this times 1 minus z times x1 to xk minus 1 minus bak. So you divide a1 over n will be this number and so on. This kind of, so from these are I want this variety, or k minus 2-dimensional variety, k minus, and so it is k minus 1-dimensional. So xy ck. Yes, I have y now. So you can consider it a kind of y something. Maybe I need to on this variety, algebraic variety, defined in an k-dimensional complex space, not compact. So what? Integers, yes, integers, yes. No, these are rational numbers, yeah. They must be. So, if you divide, so y a1 divided with m. So, yes. So in any case, on this kind of variety, I want. So how to justify on which algebraic variety we shall think about this kind of differential form? It is this kind of algebraic variety. So I simply I want to give you an idea. I'm not so precise here. Very rough. So the other thing is that we can consider it as this kind of view also. So x is small x is x1 to k minus 1, and x, and I can add one more variable and consider embed this variety in k plus 1 dimensional complex space with codimension 2. So it is y to m equals j equals 1 to k minus 1 xj aj 1 minus xj bj, and then last term will be x minus z to power xk minus ak, and the second equation is, of course, xk equals x1 power x k minus 1. Very simple equation. Very simple equation. Sometimes, so this equation is more symmetric than this one. Yeah? There are some so it has a complete intersection. Codimension 2 in k plus 1 dimensional complex space. So this kind of view can be helpful. I recommend that you to do mathematics more symmetric manner than not to be stuck to some choice of parameters, choice of coordinate systems, and so on. In fact, this many researchers somehow stack quite not so fruitful, not so productive way. Some you know that you go this way, and I have chosen this parameter space and this, and you can continue this kind of research in many years, 20 years, 30 years. Yes, I see such cases. So this is very small. I don't go further. Maybe if somebody is ready to continue this discussion further, I'll be more than happy to do this. Yeah, simply I show you what kind of differential form, what kind of differential algebraic variety we are looking at. Some what kind of, with this Pochhammer hypergeometric series can be considered as a period of which kind of algebraic variety. And you see that very symmetric form, of course. And so, and now, this was a proof of the, so I can use it. So this proposition, I prove it in making use of Bernoulli. Yes, Bernoulli or Euler-Bernoulli beta function. Euler-Bernoulli beta function. That I have. So many of you know. I think that I recorded on the very first lecture. You were absent. You were still in India. In September, maybe I. So So proof of this formula, say, interpret as interpretation of Pohama hypergeometric function is somehow constant times period integral or integral over on an algebraic variety that is defined by this, of this form. So, the first thing you shall do is simply this expression. Yes, open this. You know that the last factor. 1 minus, because we want to get a hypergeometric function depend on some parameter z. Other factors do not depend on z. No deformation. Z is deformation parameter. It's a coarse coordinate of coarse moduli space, if you want. Yes. So. And so I write it once again. Alpha j minus 1 and I open it with assuming that xj and z everything is smaller than 1, yeah. I shall write it down in a form of Taylor expansion. Minus m minus 1 divided by m factorial. And minus I have m minus z yeah, simply I opened it. So you see that immediately you see that, so the advantage is that you can integrate so what is this? This is so xj to the power alpha j minus 1 became now alpha j plus m minus 1, isn't it? Here. Alpha j xj to the power m. I have here for every j, xj. So this one does not change. This one does not change. And I have minus 1 to the power m. Here also minus 1 to the power m. So it's nothing but to see that. So I shall put it now summation m here. And so it's nothing but alpha k of Pohama symbol, isn't it? And m factorial, and z minus 1 cancels. These are m minus 1. So and z to the power m, I think. Minus 1 alpha k, yeah, m minus 1 factorial and z to the power m. Yes. So now you recall, I recall that what are that? Summation. So this was Euler-Bernoulli. Beta function. Bernoulli, yes, Daniel or Jakub. I think that it was Daniel Bernoulli. They found that almost simultaneously in 1727. Almost, it is amazing that. No, both of them are Swiss. Yeah, Switzerland. Yes, he worked in St. Petersburg for a long time, but yes, it can be that. Yes, in any case, yeah. So assume that p and q are not negative integers and so on, then so making use of this Euler-Bernoulli formula. I remember it by heart, but somehow. Yes. So sometimes we use beta, so B, PQ. This kind of notation also is used. So, so first it's P and Q are positive numbers, and then you consider analytic continuation with respect to P and Q. And it is valid so far as this expression has meaning. It is analytic continuation. In fact, in the exercise sheet 2, yes. 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 In fact, this you see that why it can be analytically continued to P and Q, PQ C2 minus Z square. Yeah, Z. What is it? Yeah. Z minus. Yes. It cannot be negative. Yeah, when gamma function has loses its meaning, so it becomes infinity. That is a P and Q, P or Q minus infinity, minus negative integer or P plus Q. It is, yeah. If P plus Q negative integer, then it is simply 0. Huh? Simply 0, I think. It becomes 0. I think so. In any case, yeah, such kind of analytic continuation argument can be used to justify first. So then in this science, it's important. Everybody asks for which parameters this formula is valid. This kind of formula is valid, like this and this. So all the time you imagine to imagine how to extend this the region of validity of the formula in making use of analytic continuation. And so far as analytic continuation is possible, every formula can be justified. Every formula, yeah, almost all, yes. I can say it, yes. And in this formula you see that the obstacle where this analytic continuation cannot be done because gamma function has poles. Where you encounter poles, you cannot continue, so justify this expression. It becomes infinity or meaningless. Otherwise it has. Okay, so small comment. Now, in making use of this formula, let us integrate this say, so this was omega alpha beta. So omega 01 k, so 01 of xj alpha j plus m minus 1 and 1 minus xj beta j minus alpha j minus 1, okay, dxj. It is nothing but this. It is nothing but gamma alpha j plus n gamma beta j minus alpha j divided by gamma summation of this, that is, say, n plus beta j, isn't it? So this plus this. Beta j plus m. I guess beta j plus m, isn't it? So this expression appears. This symmetric expression appears. So I continue further. So I'm integrating this expression, okay, on this cube, k minus one dimensional cube somehow. Okay, so this definition has been used. Yeah, everything is here. Okay. So I'm now evaluating this integral. So the integration of this this k minus 1 form over 01 k minus 1 turned into the following form. That is, say, and of course, k minus 1 of each term so summation of so this one has summation, and each term became this up to z to the power n and this factor. So I simply write it down in this form, and gamma times gamma beta j minus alpha j Okay, then times this alpha k alpha km alpha km, or I can write it down in a more symmetric manner that alpha k of m, this Pohammer symbol, was this. And m factorial. M factorial is nothing but, okay, m factorial. It's z to the power m. So this is the result. This is the result. What is the difference between, so, I want to tell you that, so these two expressions are the same up to multiplication by factor that you can calculate quite easily. So beta j, gamma j, beta j, yes. You say that what is lacking here is this and this, this and this. Is in this. So if I multiply by this factor, no, let me multiply this factor also, and divide this. I don't have it. This I don't have it here. So so it doesn't depend on m. That is, say, times k minus 1 gamma and times this. Gamma let me and also I don't have here alpha k, isn't it? Alpha alpha k don't have it. So this one is nothing but beta k. So in terms of this 1 plus m, beta k plus, what is this? I know that this is this. Yeah, beta k plus is equals to m factorial. So, in fact, in this manner, you see that two of them after this multiplication k minus 1. So what is this? Yes, k minus 1 and k. I don't have, what is k? Alpha k. Sorry. Alpha till alpha k minus 1, and then I have alpha k. That is, say, gamma alpha k and gamma beta k. That is, it's 1 in fact. So in this manner, I get the formula that shows heavy rays. Now, in the upshot was 0, 1, k minus 1, omega alpha beta times in fact, this one is a bit long. Yeah, this one is gamma beta j over gamma alpha j, gamma beta j minus alpha j. Equals this Pochhammer hypergeometric series. Okay. So, in fact, the lesson of this calculation is rather to see that this generalization, very seemingly simply-minded generalization of this series, has a generalization, has in its background, generalization of variety, algebraic variety, on which you consider this kind of integral, that's a periods. Gauss case was simply the algebraic curve of this type, and now Pochhammer case, Pochhammer hypergeometric series allows us to consider algebraic variety of higher dimension. So this is the so how late it is? Yeah, now I have 10 minutes or so. So yes, and you remember that now to justify this procedures somehow. So I'm writing here as gamma z. Yes, the gamma z was gamma depending on z was cycle of this variety over, say, yes. In fact, we were talking about this, but rather we draw it, but we allowed coefficient as coefficient field C, that is say so I gave you this exercise. In general, we have far more cycles in this Z model than the dimension, the rank of this Z model is far higher than C model here. So, in other words, the cycle that are distinct here over Z, maybe so C1 gamma 1 plus C2 gamma 2. That may not be 0. That may not 0. But if you allow this coefficient to be complex, this cycle may turn out to be zero homologous. C1, C2. So I wanted to draw your attention to this situation in giving with data with exercise. With data with exercise, I propose. So the example was this. So y is 4. Yeah, maybe like this. I square plus x plus 1. I consider this kind of curve. So m equals 4 and x equals, so these are z now minus 1, so 1 minus x, 1 plus x, say. No, it doesn't matter, x square. If you want, I can put it minus 1, yeah. It doesn't matter much, so it's everything complex. And the first question is, of course, it has dimension, this, so H1Z, this has rank 2. That I have shown with data of maybe I need to more cycles. So how I've shown it? I've shown it in the following manner. So this this integral, so yx has branching points 0, 1, 1 over z, and infinity. And we consider, so normally we have pq yx dx, so why is this? Or it is exactly the case of omega alpha beta in two-dimensional k minus 1 equals 1. One case. So PQ, as PQ I have 4 selections. PAQ, these are P and Q on 0, 1, 1 over z, infinity, this pair, minus P equals, and there are 6 for C for 2 to choose two such points, to such interval, connecting P and Q. We have 6 choices, but we have only 2 dimension 2-dimensional same model as, and that is the reason why this the Gauss-Hypergeometric equation has order 2 differential equation. Yeah. So that means that these are many of we have chosen. For example, we have chosen this kind of 0, 1, and so 1 over z, infinity, like this. This kind of cycles we have chosen. Maybe this was F1 and F2. So the fact is that the cycles like this, I have here infinity 0 cycle, let's say that interval 0, 1 over z, here 1 over z infinity. These are linearly dependent. That is, say the summation of these cycles gives you 0, because it's so homologous. You see that it's 0 homologous. These 3 say chains. I don't know, somehow a bit unique. And it is true also here for these 3 cycles, 0, 1, 1, 1 over z, and 1 over z, 0 to 1 over z. These coefficients are. And I have also, here I have such kind of relation. There are 4 relations between these 6 integrals. But 4 relations are considered here, and C over C. That is, say, I consider this kind of equivalence relation, homologous 0 relation, because if I down here, it will be e to the power 2 pi I times, say something like 1 minus gamma, I think. This will be multiplied. So the argument, if this is real, then this interval will have this kind of argument change. And if you compare this and this cycle 0, 1 cycle, 0, 1 cycle here, they may have different argument, complex argument. So in this way, I have, yeah, exactly. There are 3 C1 gamma 1 tilde plus C2 gamma 2 tilde plus C3 gamma 3 tilde. So if you want to, this gamma 1 is here, and something, yeah, this Kappa cycle, and it's gamma 1 0, 0, 1. Yeah, we are looking at on P1. Somehow P1 minus, and the covering of P1 minus 0, 1 infinity covering. Yeah, there. Yes. 0, 1, oh, sorry, 1 over that. So no, there is no distinction between. In fact, it is reflected on the level of complex number multiplication. Yes, it's a bit complicated. So I don't go into detail to them now. The idea is this: that there are 4 relations between 6 cycles. Between 6 cycles, 4 complex coefficient relations. Okay? These are complex C1, no. Rather tilde here. So C1, C1 tilde, C2 tilde, C3 tilde, these are in complex. And the complex number comes from the argument change around each branching point. So in fact, this cycle, this interval, they have different arguments and complex arguments. So there are 4 relationships. So 6 minus 4 will give you 2. That is the dimension of complex dimension of so, but like this example, I encourage you to think over this example. That is, yeah. So the point is that I consider this curve in C2, not in P1, not in P2. So infinity is not, it is not allowed y or x be infinity. That is, you shall exclude these infinity points from the curve of so compact Algebraic curve that you maybe you are accustomed to look at. Yes. And the result is that, so this on Z, it has, so this one, rank of H1 Vz of Z will be 5. In fact, it can be explained like this. So it is, I think that is so. Singular elliptic genus 1 curve. Genus 1 curve has usually alpha beta cycles. Of course it has, but there are points. How many points do I? So maybe I need to exclude 4 points at infinity. So that comes from here. Yeah. You see that. So where in it? Yes. So 4 points I need to exclude because these infinity points. Infinity e to the power, so y to the power 4. So at infinity this equals x4, isn't it? So I have 4 branches. Nearly at infinity. At infinity. So you have four irreducible branches near infinity, and they are distinct. That is, say, infinity and minus infinity and I infinity minus I infinity. I have 4 points to exclude. But the cycle that are turning around all these, so I have 4 cycles here, but these 4 cycles are linearly dependent, because if I turn all of them, all on them, then it will be it will be so summation of say gamma infinity infinities. There are four infinities. Infinity 1, maybe I to the power minus 1 to the power L, say, like this. Summation L equals 0 to how much? I have 3, eh? No? I minus I, and so I want to get 1, this will be 4, 0 will give me, so 1, yes, there are 3, yes. Square root of minus 1 I to the power L, from L runs from 0 to 3. So these are characterized, these cycles can be characterized in such a manner. Yes, I to the power L, yes. The summation of all these will be homologous to some C1, C2, I cannot say which one, but you see from this figure that it is homologous to a cycle that is that comes from alpha beta. This usual cycle that comes from the compact algebraic curve alpha plus beta alpha something, yes. There's C1, C2. That is, say, the summation, there is one relation. This is, that even though these are names, so the coefficient is 1. Summation of all this with coefficient 1 will give you some cycle over Z, over C1, C2, of course, it is over Z. That is, everything is Z. Integer coefficient relation, this is, between these 6 cycles. That is, say, the rank of this Z module is not 6, even though we see 6 cycles. There is one relation, and only one relation. You can easily see that any other linear combination cannot be homologous to, cannot give a zero homologous cycle. That is, say, this 6 comes from, this 5 comes from the following consideration, that I'm explaining you the solution, almost a solution to the exercise. So I have 6 cycles. Yeah, 6 cycles. So 2 that comes from alpha and beta, the compact, from compact genus 1 curve, compact genus 1 curve that everybody knows, and there are 4 cycles that comes from this decomposition y minus x I. So from infinity cycles around different infinity points. Yeah, there are 4 points. But there's one relationship. Relation between so gamma infinity cycles over z. So everything is over z. The important thing is that that will give you 5. Okay, and of course this is greater than 2. 2 we have yes, in VZC complex coefficients we saw only 2 cycles. Yeah, because we allow us too much equivalence relations between different cycles. So this is a kind of sacrifice we pay to get somehow understandable, easily understandable theory. So this one, so rank 2. Then we think we can monodromy and so on. We could calculate. We could do it on 2-dimensional vector space. 2-dimensional vector space. Huh? Everything, yes, till last week. Yes. But in fact, our challenge, our really geometric problem is rather to understand this. To understand this. So there is a difference between C coefficient homology, C module. So homology as C module and homology as Z module. Yeah. There is Z module, Q module, the same. Yeah, of course. Yeah, coefficients. We can consider as a Q module. Yes, if you, it can be simple. So this is the difference, and as for the geometry of this kind of, where is it? Yeah, this kind of algebraic variety, we cannot go into this kind of story, yes, this kind of precise description of that. We always consider C model, C model homology, and so on. Yes. But the point is that, yeah, I began to explain this because I wanted to understand this one as rather this differential operator, after application of differential operator, this cycle, so not only 0-1 cycle, 0-1 somehow Pohama cycle, kind of cycle constructed from this kind of cube, but we can see for other cycles also simply I wanted to say this. There exists, we can, it's true that there is a, so this is k-1 form, k-1 form. There exists k-2 form, such that omega, so after application of this differential operator, yeah, Pochhammer hypergeometric differential operator, you can change the order of differentiation, and so in fact you apply this, the alpha betas here, the of alpha beta here. After your calculation, you see that there is a k minus 2 form, keep k minus 2 form. So omega alpha beta, after application, it becomes an exact form. The result will be exact. So simply, if you apply the alpha beta here, it will be exact. I think that for the case of Gauss, I put it in the exercise now. Drum cohomology understanding of this. Yes, I think that I put it, and it is the similar thing. You can do it for the case of this variety. Yeah. And see that this is a drum exact form, so it is, so every C that is H k minus how many? K minus 2 with Z, of course, over C for every cycle, yeah, for every cycle. It is true that you can consider by Stokes theorem, Stokes theorem, and you can identify it equals to a boundary of this cycle, and that is equals to 0. Yes. Sorry. No. Yeah. This is somehow the story of wait a minute. So where omega alpha beta equals d of exact form, and so yeah, and this is 0. It is close, and it is, so you need to justify this. Consider kind of Pochhammer cycle for this, but the consideration is this. The rough idea. So that is so what I want to say is that what we should consider is not only this kind of cycle that is constructed from this real cube of dimension k minus 1, but also cycles that are related to this factor also. Yeah. Such kind of integral also is also solution to the hypergeometric Pochhammer hypergeometric equation. Yes. This is also that is solution is also a solution to Pochhammer hypergeometric equation. So next week we next week we continue the analysis of this differential equation, this solution space to this differential equation that has rank k, already rank k, rank K. And yeah, quite many applications to transcendental algebraic geometry, including mirror symmetry. So, so for this purpose, I need to prepare some analytic tools to analyze solution space. So that will be the next. So that's subject of lectures till the end of this semester. Yeah. Okay.